Hello and welcome to Bedroom Physics. This is the example video for mechanical waves. The first problem that I'm going to be doing is like a general wave problem. We're solving for period, frequency, wavelength, etc. Just kind of a general idea of a wave. And the second problem, we're going to step it up and do a torque problem. Let's jump right in. Okay, so the story for this one is we have a string and it has a length of 50 centimeters. And it's oscillating, and there's a strobe light that is flashing at 83.3 hertz, and this is the same string for the first 5 flashes. So initially the string is here, the strobe light flashes, then it's at 2, strobe light flashes, it's at 3, strobe light flashes is at 4, strobe light flashes is at 5, and so on, so on. What we want to solve for is the period, the frequency, the wavelength, the normal mode, the propagation velocity, v in the y direction at the first interval, and velocity in the y direction at the third interval. And lastly, we want to solve for the mass of the string. Okay, so for the period, we know that the strobe light is flashing at 83.3 hertz. And every time it flashes, it's at these new positions. So what we're going to do is we're going to find the period of the flash, and then we're going to multiply it by however many phases there are in this oscillation until it's back where it started. So if we're here at t is 0, then this is t is 1, t is 2, t3, t4, t5, t6, t7, and t8. So we're going to invert the frequency of the strobe light and multiply it by 8, and I believe the period for this period for L is equal to 0.012 seconds, and when we multiply it by 8, we're going to get 0.096 seconds, and that's going to be our period of the string. And of course, frequency is 1 over the period. So we're going to do frequency of the string is equal to 1 over 0.096 seconds, which is going to be roughly 10.4 hertz. Okay, so we solve for the period of the string, we solve for the frequency of the string, now we want to solve for the wavelength. And we can do this graphically. We see that one cycle of the wave is 50 centimeters long, so our wavelength is going to be 50 centimeters. Okay, and the normal mode, so we can also solve this one graphically. We know that at the first normal mode, the nodes of the strings would be at either end, but here we see that we have 3 nodes, one at x equals 0, one at 25 centimeters, and one at 50 centimeters, and this makes it a full wavelength. So n is going to be equal to 2, because after all, we're looking at it 1 over 2L. That was in the concept video, of course. So n equals 2. Okay, velocity in the x direction, or the propagation velocity. How are we going to solve for this one? We have wavelength and we have frequency, and wavelength times frequency equals velocity. Wavelength times frequency of the string is equal to velocity, which is going to be 10.4 hertz times 50 centimeters, and I believe it's going to come out to roughly 5.21 meters per second. Okay, so now we have the period, the frequency, the wavelength, the normal mode, and the velocity, the propagation velocity. Now we want to find velocity in the y direction at the first interval, and also at the third interval. And in the concept video, we went over the derivation for v of y. But here in this problem, if we look at it graphically, the interval at the first time is at an max, so sine is going to be equal to 1. So v of y at 1 is just going to be equal to the amplitude times the angular frequency, which is going to be 1.5 centimeters times 2 pi times 10.4 hertz, which is going to be equal to roughly 0.982 meters per second. Oh, I accidentally wrote an M here. And then Vy at 3, well here sine is making the amplitude 0. So everything is just going to cancel out to 0. So Vy at 3 is equal to 0 meters per second. And the mass we can solve with the relationship V equals the square root of tension over mu. And so we're going to have V equals square root tension over mu. And then we're going to do V squared over T equals mu. But mu is equal to mass over the length. And so we're going to have T over V squared times length equals mass. And that's going to be equal to 1 Newton over 5.21 meters per second squared times 50 centimeters is going to be equal to roughly 0.0184 kilograms. Alright, on to the next problem. Okay, so for this next problem, we have a bar that's attached to the wall. It has a 30-degree angle between the wall and this bar. And the bar is attached at the top by a string that has a length of 0.33 meters and a mass of 0.092 kilograms. The bar itself weighs 45 kilograms, and what we're trying to find here is the fundamental frequency, or Fn, when n is equal to 1. Okay, so how do we approach this problem? Well, we know that in order to find or solve for the frequency, we're going to need velocity and we're going to need the wavelength. We kind of already have the wavelength. After all, the wavelength in terms of the normal modes of a string is 2L over n. And since n is 1 in this case, it's just going to be 2L. So essentially, we just need to solve for velocity, and we're going to need the tension for that. We have mass and length of the string, which is going to give us the linear mass density. So all we need to do is solve for tension. And in this case, we can't just use normal vectors. It's not static in a way. I mean, it's not moving, but there are torques that we're going to have to add up here to solve for the tension. Okay, so if we use this end here as a hinge, then we're going to have the mass gravity at the center of the bar, and we're going to have the torque of the string at the very end. So the sum of our torques is going to be equal to mg length of the bar over 2 times sine of, and we're going to want to line up the forces. So since the cosine of 60 degrees is perpendicular to mg, we're going to do cosine of 60 degrees. I mean, you could probably do sine of 30 degrees. It's easier for me. And I'm going to add tension, and it's at the end of the bar, and it's horizontal, so we're going to need sine of 60 degrees. Okay, and that's equal to 0 as it's not moving. Okay, so now we're just going to move everything over and solve for t. So we're going to have, and we're going to cancel out L's, And we're going to have negative mg over 2 cosine of 60 degrees divided by sine of 60 degrees. That's going to be equal to negative mass gravity over 2 cotangent of 60 degrees, and that's going to be equal to t. And I believe that when you plug in mass 45 kilograms, gravity negative 9.8 meters per second squared, and cotangent of 60 degrees, we're going to get roughly 127 newtons. Okay, so now we have that. We can solve for the frequency, and we're going to have frequency 1 is equal to, okay, so it's tension over the mass of the string times the length of the string under square root over 2 times the length of the string. So 127 newtons over 0.092 kilograms times 0.33 meters rooted over 2 times 0.33 meters, and it's going to be equal to approximately 32.3 hertz. Alright, in any case, this has been the example video for mechanical waves. Hope to see you in the next concept video, hopefully on Thursday, where I talk about sound waves.